I think for
Oh,
most people who
yes.
use silver, they're not operating at that level, and so they may not even know about a dendrite issue. The number one concern I see brought up about silver is just the corrosion with tarnishing.
Yeah, so that is something at the time of assembly. So
Sure.
I think it is very, very critical because it is referred as a 6 months shelf life. But when you are in a 4 or 5 months range, you start to see tarnishing of silver, and that actually affects your assembly process. So that is sort of an early stage issue with the tarnishing, and then the dendrite is sort of after assembly an application stage issue with dendrites.
Hello, everyone, and welcome to the Altium OnTrack Podcast. I'm your host, Zach Peterson. Today, we are talking with Kunal Shah, president of liloTree. We've had Kunal on the show before, and today we're going to be talking to him about an upcoming SMTA panel that he is part of, and I'm very excited to learn more about what he will be speaking on. Kunal, thanks so much for being back with us today.
Absolutely, Zach. Again, the last time our discussion was really intriguing, and I think it's always great and intriguing discussion with you. So thanks for having me.
Well, thank you very much. You know, there have been a lot of, it feels like a whirlwind of developments over the last couple of years. And
Yes.
one of the big areas where we've seen a lot of development is in the push towards UHDI, especially here in the United States. And so that is
Yes.
our perfect segue into the broad topic of what's going on with an upcoming SMTA panel
Yes.
on March 26th, where you will be speaking.
Yes.
So if you could, just give us a brief overview of what's going on at that panel and what you'll be talking about.
Yeah, so no, it is very interesting as you brought it up. UHDI, which is ultra high density interconnects in the electronic industry, is becoming sort of one of the fastest growing area, especially as you mentioned in United States, and one of the things also from a perspective of defense and some of the high reliability application. UHDI is becoming it is becoming a norm, so to say. So some of the new development, especially from the processing perspective to the material perspective, is something that's been going on past couple of years significantly. And I think if you and I'm slightly digressing from the topic of being giving you overview. If you look at a little bit of history, we've been doing a very high line spacing in terms of into 100 micron to 50 micron line spacing very, very commonly. Now we are entering into a HDI and ultra HDI where these dimensions are getting literally into sub 20, sub 10 micron range, where a traditional processes are not something that you can use. So you have to innovate in terms of the processes and material to make these UHDI designs and the fabrication available or sort of even possible. So my talk, coming back to your specific question, my topic is actually going to be how the surface finishes or the plating or a treatment that you do on top, which is a final layer, a conductive treatment that you do on top of these UHDI line spacing interconnects is what I'm going to be talking about. What are the things one should be aware of? What are the things a traditional technology may not work, and why a newer technology will provide you even the possibility of UHDI processing at sub 20 micron, sub 10 micron range, and also how will you even increase the reliability and sustainability, which is also critical part when you are dealing with high reliability defense or medical electronics, so on and so forth.
You had mentioned traditional processes. I'm going to assume this refers to the traditional plating materials that might be used in standard fabrication. So let's say, tin lead at
Yeah,
the low end, or not tin lead, but immersion tin maybe, and then all the way up to like
yeah,
EMIG
yeah,
or hard gold or something at the high
yeah.
end.
Yeah, absolutely. What you brought up is absolutely accurate. Immersion tin, as we know, historically has been one of the most popular surface finishes when you talk about 90s and early 2000. But whenever I know, I always go back to history because that actually teaches so many lessons and sort of understand what are the reason for us to innovate. So what happened at early 2000 when these micro BGAs started coming, where surface planarity becomes the most critical aspect. An immersion tin, and also from immersion tin, which from the hassle into immersion tin, some of the ROHAs sort of got kicked in, where lead was a standard norm, and when the ROHAs came in, the lead sort of started to phase out, and then immersion tin with lead free was not something reliable, and a lot of other issues. So that's when people started pre- predominantly started moving towards ENIG, that is electroless immersion gold, just a full form of ENIG. Um, what are the benefits of ENIG is, one, it gives you extremely good surface planarity because of the nickel layer and the gold layer. The surface roughness is extremely planar. The surface roughness is very low. So that is something from micro BGA assembly and all those things was very, very good. And also with the gold based surface finish, it gives you more breathing room in terms of shelf life. So for example, your boards are being manufactured one part of the world and assembly is happening another part of the world, and especially you have supply chain logistics issues going all over the place. If you are not able to, like immersion tin or OSP or some of the other hassle, you're looking at a shelf life 3 months, 6 months, roundabout in that range. However, when ENIC got introduced, you could have anywhere from 12 to 24 months shelf life. So it gave you a much more freedom in terms of doing assembly and bareboard manufacturing, sort of, in terms of the planning out how you're going to do logistics. However, as we are moving into UHDI, uh, when you have ENIG, that's what I'm going to be actually focusing on in the present in our session on March 26th, which is the part of SMTA, on focusing on UHDI, because what happens is some of these copper is not traditional copper plating. It's using some sort of SAP, semi-additive process, or MSAP processes, as you may have heard. So what happens that it actually puts some sort of a palladium ink or palladium layer wherever you want these feature to populate, and then you have some sort of a copper process that gets deposited on top of these palladium catalysts. What happens that is there is still a palladium. So even if you populate these copper, it's not exactly right. Like for example, if you have 5 micron spacing or a 10 micron spacing, but your feature, the palladium is slightly bleeding out of your feature. So palladium, and then the copper is also slightly bleeding out because palladium is bled out from the defined area of these features, conductive features, which is copper. So it's not. So when you have a subtractive process, because of the laser, it is clear cut uh, removal of copper and palladium underneath, right? However, this is a chemical based additive process. You have this bled out area from the feature itself. So I'm going a little bit of a technical, but it is important for a listener to understand that when the problem when comes, that when you are trying to do nickel, it will look for this copper and it will plate everywhere. So this bled out area will also be plated, which is almost like overplating. You don't want plating on those areas. But nickel doesn't understand, should I be plating onto the actual feature or should I be plating onto the bled out area? Both are identical copper. So wherever it sees copper is going to plate. But when you actually end up seeing under these highly magnified microscopes, it's only when you see it with naked eye, it looks all perfect. But when you see it these magnification lenses, you see these nickel is being plated in a bled out area also. Now what if your features are so close to each other that the bled out area of one feature and another feature almost coalesce or talk to each other. So you almost have a bridging issue. So some of these, so nickel plating becomes extremely difficult when you have feature sizes into 20 micron or sub 20 micron, 1010 or 510 or 55 is, even a substrate like technologies that we have worked with recently with some of the customers, they are actually moving towards 55, which is something a few years down the road for most of the mass manufacturing, but people have already started looking into that. So when you have these features, even 5 micron, you cannot see it in a regular microscope. You actually have to put under the scanning electron, like an electron microscope of some sort. So when you go into these realm of such a minute feature, understanding what your chemistry is doing and what are these pitfalls. So I may have digressed and sort of started giving a lot of information, but I hope I was making sense.
Yeah, just to maybe briefly summarize some of the issues here that arise at UHDI. You're bringing up a line spacing issue where you can have excess plating or overplating, and then there's
Yeah.
also the planarity issue. Obviously, not such of an issue when you have coarse pitch BGAs, but once you start going to very fine pitch BGAs where you have high density, high IO count, or just maybe it's low IO count, but everything is very dense. Sort of the
Yes.
corollary to the plating issue. And then I
Yes.
think there may be a third issue here, which you haven't mentioned, but it's maybe from the SI perspective, which is
Oh yeah.
depending on the plating
Yes.
material you use, when you have very
Yes.
thin
Yes.
traces, you have much more skin
Yes.
effect, and there's more skin effect in the plating. So now you have a loss issue, especially when you're using nickel
Yes.
platings.
Absolutely. So I think thanks for bringing that up. I was going to get to that point that what happens that one, you have a nickel which is conductivity. So I give you a little bit of technical background of why nickel is so detrimental for signal integrity is because when you have copper, which is one of the best conductor that we have, and that's why one of the reasons we have that being prevalently used everywhere in entire printed circuit board and semiconductor electronics industry, right? But then when you plate nickel, usually signal passes through the top layer of your conductor. So when you plate whatever is the top layer, and then it has a skin effect. So your top layer is say for a gold, but gold is only 50 nanometer. Your skin depth is about a couple of micron, depending on your frequency range. Most of your signal passes through nickel. Now, what if your conductivity of not what if nickel's conductivity is 1/4 of the conductivity of copper. So think about what will happen to that signal. It is significantly slower for that exact same reason. It actually makes even worse when you have UHDI. So I'm talking about these standard PCBs where everything is coarse. But what if things started come close to each other? Then nickel on top of having a low conductivity is ferromagnetic material. So it actually starts creating a magnetic interference also because these features are so close to each other. A magnetic field of one feature will sort of overlap a magnetic field of another feature. So you have a basically a magnetic interference is also being created that is also detrimental to a signal integrity. So something that is um, completely ruin the performance of the designer when they're designing on the computer, and then when you are actually manufacturing with the surface finish, all these effects will actually detriment the performance of signal integrity that you actually designed for.
And then regarding the overplating issue, just for a moment, right? I mean, if you're at high enough bandwidth, you're going to notice the impedance deviation along that line. But one thing I'm wondering is there like an overplating compensation that's performed in manufacturing? Because if you think about with standard subtractive manufacturing, right, we do an etch compensation, right, to account for the trapezoidal appearance of the real traces when they're actually printed. I'm wondering, is there like an overplating compensation that's applied as well?
So a lot of these things are I mean, you can always design for compensation, but then things become so difficult because some of these overplating is in the less than 1 micron or micron and a half and a couple of micron. It is that small level. But when I'm talking about in the scenarios where you are literally the line spacing is 5 micron, so a 1.5 couple of micron overplating on one side and another 1.5 couple of micron overplating on other side, there is a chance that things may go out of control and having a bridging issue. And something that overplating may actually so you can design and have very accurate way of how you put palladium ink or palladium layer underneath. But again, these things are you are talking about managing micron a couple of micron layer or level accuracy, which is extremely difficult. So yeah, we have had customers, especially using MSAP processes, complain and share some of these issues when they try to plate nickel. They try to do compensation, but again, the technology is still evolving from 20 micron into 10 micron. They're trying to play with it, but it's getting difficult as we move into smaller and smaller feature sizes.
So what are some of the solutions here to deal with this? I mean, there's such a big drive to go to smaller line widths, smaller tray sizes. We're always trying to fit more stuff
Yes.
into a smaller area, and I think packaging is one thing that's going to continue to drive this trend, especially as chips start getting built in 3D. So now you have even more stuff you have to pack into a smaller area. So what are some of the solutions to this? Because it sounds like at some point the old solution in the traditional fabrication world of just space your stuff out a little bit more starts to go out the window.
Absolutely. So, Zach, I think you brought up a couple of points, and I'll get to the solution. But you brought up a good point where, as you mentioned, that as we are trying to go into more and more dense designs and the features and much smaller features and denser, and we are actually moving. So we are moving, as you brought up, from printed circuit boards to almost like a substrate, like almost to into the packaging world. So what we are seeing is a semiconductor packaging manufacturing and printed circuit board almost started to overlap, where a lot of companies in America have started and have plans to start doing substrate like manufacturing and having these UHDI capabilities available. Coming back to a surface finish solution, that what are the solution for the existing conventional technology, as we talked about, that is ENIG, which are available. So one of the things, so I'll get into explanation of what is the background of ENIG. Why do we even use ENIG, right? So the best reason why we are using ENIG is gold. The gold layer is it's a noble metal, so it doesn't do any chemical reaction with any element. So that's why it's noble. So that's why you have a final layer of gold, and that's why shelf life for 12 to 24 months because of the gold layer. Also, gold provide you extremely planar surface with a very low surface roughness. So that is a second benefit, which is both are extremely beneficial, especially into a UHDI application. But then you cannot plate gold directly on top of copper, because what happens that the copper will start diffusing through the gold, because there is no way copper is being stopped, and then copper will come to the surface of gold, and then it compromises the conductor altogether. And that's why nickel is used as a so-called barrier layer. And that is why ENIG has become so prevalently popular, because they put a layer 3 to 6 micron of nickel and then put gold. Now, since we discussed that having nickel is such a detrimental from a surface, signal integrity perspective, and also from a perspective of plating and overplating, and even managing UHDI plating a nickel on top of those structures are extremely difficult. So, what is the solution? So, solution is actually liloTree has innovated one of the products called barrier layer, which is not a nickel-based barrier layer, but it's an organic solution treatment, which actually is not adding a layer on top of copper, but it actually passivates the copper layer on the top. So what I was suggesting, that why is nickel used? Because nickel is used as a barrier layer. The copper is prevented to diffuse out of nickel into the gold. The liloTree's barrier layer treatment is actually a treatment conducted on top of copper that actually does exact same thing without the need for a nickel layer. So that is actually very, very beneficial, because you're not adding a layer. The plating process is extremely stable, and you don't have to have this issue of overplating and so on and so forth. It actually only treats the copper layer wherever it is defined, right? And the best part is it does not compromise the copper conductivity. So pretty much you are getting, and when you have a only 50 nanometer of gold after the treatment is conducted on top of copper. So basically you are getting all the benefits of ENIG without the need of ENIG, because the barrier layer is acting as a nickel for providing that barrier for that copper diffusion. But on top of it, the benefits are signal integrity is as good as a best conductor, which is copper, because you have only 50 nanometer, but your skin depth is about 2-3 microns. So most of your signal passes through copper, which is the ideal thing that you want. And then there are no plating issue or overplating issues with the barrier layer and the gold. So those are some of the benefits, because you are not using nickel, but it's this organic based solution treatment is actually providing that barrier layer, but giving you all the benefits that how the nickel is playing detrimental effects off.
So has anyone looked into some of the other plating options for UHDI, such as like silver or OSP? I bring up silver because this is one area where I've had a little bit of experience, which is where you have a digital section and a really high frequency RF section in the same board. And with RF, one of the go-to options is usually silver, because we're trying to reduce that insertion loss that would come from something like ENIG, but maybe we want a little bit longer shelf life than something like OSP.
Absolutely. So wonderful point. I mean, immersion silver has been a go-to surface finish or a plating option for anything RF or high frequency. Reason why is silver actually has even higher conductivity than copper. So that actually gives you the best signal integrity possible. Like the best you can actually get with silver. The problem with immersion silver is the overall environmental reliability. So for example, if your surface finish or a portion of your surface finish is left behind in the assembly, right? If any of the pad or so even if your pad is, say for example, this size, I'll do some hand gesturing. Your pad is this size and your component is this size. There is an exposed surface finish left behind, a slight or few micron. Silver actually has a tendency to create or do chemical reaction with sulfur and form something called silver sulfide, and they actually then starts forming dendrites. So within year or 2 years in the environment out in open, this dendrite will start forming and start growing, and then it may actually create exactly the bridging. A dendrite from another pad and dendrite for this pad will merge and create a bridging issue. So then you will start having a malfunctioning issue because of these dendrites. So these environmental corrosion issues with the silver is something that one has to keep in mind. And that is why I think it's a great discussion. We had this discussion last time, that when we talk to a designer and the materials company and the fabrication material that are used for the PCB and the assembly, it is important for a collaboration, because not knowing how and where it is going to be used in the end application, it actually can be in a very tricky situation, because you are designing for one reason, but then when it's applied, all the factors that one has to pay attention to, that where is it going to be used, what are the environmental conditions. For example, when you are using somewhere in Asia or some parts of the Europe, the environmental condition, the levels of these gases, including sulfur, are much higher than other parts of the world. So understanding all of these issues, and then the temperature and the humidity bias also with silver can actually lead to these dendrites growth even faster. So understanding these corrosion issues, and that is why a gold-based surface finish is still a prevalent. Of course, as you brought it up, ENIG has been prevalent, but when you come to RF, people is like, oh, just do immersion silver. But you also have to understand some of the reliability concerns with immersion silver that it brings about.
Yeah, and for all the times that I've used silver, it's never been in a UHDI application.
Okay.
It's been in applications where you have BGAs, but certainly not, sub 1 mil, let's say, line width and spacing. When you
Yes.
get to that level, I can really see dendrites being an issue. I think for
Oh,
most people who
yes.
use silver, they're not operating at that level, and so they may not even know about a dendrite issue. The number one concern I see brought up about silver is just the corrosion with tarnishing.
Yeah, so that is something at the time of assembly. So
Sure.
I think it is very very critical because it is referred as a 6 months shelf life. But when you are in a 4 or 5 months range, you start to see tarnishing of silver, and that actually affects your assembly process. So that is sort of an early stage issue with the tarnishing, and then the dendrite is sort of after assembly an application stage issue with dendrites. So sort of from a both perspective, corrosion before assembly and corrosion and dendrite after in the application after assembly is something that one has to keep in mind in terms of immersion silver. And that's why we always prefer no, I mean, we as a chemical supplier, but whenever we have to recommend for these high application, high reliability. When I say high application, high reliability application, especially now going into UHDI, because when the dendrites become even a bigger issue, a gold-based surface finish is something that we recommend, because one of the reasons is exactly because there are no dendrites. Gold will remain as is. So even you brought up OSP also. So I'll touch upon OSP as well. It's exactly that. OSP's shelf life is only about 3 months, is what is rated, right? And the second thing with OSP and immersion silver, both from immersion silver tarnishing, but even from a assembly perspective, how many reflow cycle that you have to you are going to be incurring, right? With OSP, it is a polymeric layer on top of copper. So when you put 265 degrees Celsius in an assembly, first or second reflow, the OSP is more or less sort of evaporated or decomposed, however you term it, but it gets compromised is what I'm saying. So underneath, copper is being exposed at high temperature, and it can get and likely to get oxidized. So when you go into third or fourth reflow cycle, your surface is already compromised, and you expect it to wet and perform the assembly operation on those compromised surfaces. Yeah, the likelihood of failures could be high. So OSP has that issue of um, how many reflow cycle you can run. Even immersion silver, it gets tarnished, and maybe after second or third reflow, it may not give you similar performance to with immersion silver as you were getting on the first reflow. So those are some of the issues with OSP and immersion silver. Also, one of the other aspect one has to also understand with OSP, because we are working with one of the customers and their requirement is, hey, the pads have to be conductive. So surface finish is not area where they have to be surface mounted. There are a lot of other applications, a lot of areas where the surface finish remains as a conductive conductor, staying as exposed on the printed circuit board for whatever application and reasons. But if you have OSP, the pad becomes non-conductive because it's a polymer layer on top of your PCB. So that is something that you also have to keep in mind with respect to OSP.
Yeah, I see. I think the number of reflow passes is definitely something where the designers don't really think about it because they're not looking at it from the assembly standpoint. They don't know how they're going to plan it out.
Yeah,
I do think a lot of designers will just, click the tin lead button, or not the tin lead, but the immersion tin button on their quote form online, or they'll click the ENIG
yeah,
button and they'll just say,
yeah.
yeah, go for it.
And I don't know, maybe if I can make this comment, they click on a button. I don't know from a designer perspective or from placing an order at PCB. fab house, whatever is cheapest, right? So let's pick the one which is the cheapest. Uh, because nowadays everything is an online application where you are filling out all the forms with the drag down options, and all right, whichever is the cheapest, let's pick that. But yeah, I mean, you have to, some of the thing is, yes, one has to know the reflow passes, as you brought up. Second is the cost, but you have to be very judicious of cost, because there are other surface finishes that I can bring up, like enipig, if you may be aware of, because a lot of time with the higher reliability application, palladium layer is put between nickel and gold, and one of the reasons is the black pad with enig is historically a corrosion between nickel and gold layer at that interface, and to prevent that, palladium layer was introduced, and that is why enipig is what is called electroless nickel, electroless palladium immersion gold is the full form of that. Now the cost will be even extremely higher, exponentially higher, is because the palladium layer, because of the precious metal like palladium, which is 1.5 times the cost of gold. So you are not adding the cost of gold, but on top of it you are adding the cost of palladium. So it's not but not necessary you get all the reliability with enipig. There are issues with signal integrity, there are issues with some of the reliability depending on the palladium layer thickness, and so on and so forth. So it's not that you get you pay the highest money, you get the best product, and it's not that if I select the cheapest and I'll get away with it. So one has to understand the pros and cons of each aspect, and spend wisely to get the optimal performance that one should get, especially understanding where it's going to be applied, who is your customer, so on and so forth.
Yeah, you used a term that I think is often misunderstood, which is best product, right? Best always comes with a big asterisk, because when you look at it from enig, right, best really means what? Highest reliability. Whereas you look at it from the silver perspective, best means signal integrity and not necessarily
Signal
reliability.
integrity.
So I guess
Yes.
best really takes some consideration here. And then also, I think as we get into UHDI, we're pushing more and more and more into the higher frequency range. So,
Yes.
below, let's say, a gigahertz, you're probably not going to notice the loss difference between enig and tin. You just care about the reliability. But once you get
Exactly.
into the many gigahertz bandwidth range,
Yes.
now you definitely notice.
Absolutely, Zach. So you brought up an amazing point, because even not even a gig, even up till 5 to 10 gigahertz, you may not see a major detrimental effect between enig or immersion silver or any other surface finishes. They would be all from surface finish perspective, they would be all being same in terms of how much loss that you are getting. However, as you go into 10 gigahertz to 25 gigahertz, that is where the high band of 5G is. The 77 gigahertz is the automotive, frequency, where those are the typical frequency in the automotive application. And then some of the RF is 100 plus gigahertz. So when exactly what you brought up, that when you go into 10 plus gigahertz, you will actually start seeing the effects of if you put enig versus if you put immersion silver. And that's when you have to realize that, hey, for reliability, should I go enig? But even there are concerns from the reliability side with enig. That is a different story altogether, but it is still more reliable from a gold layer perspective and environmental corrosion perspective, because it's, at the end of the day, it's a gold outer layer, right? But when you put immersion silver with high frequency, then reliability is major concern from a perspective of environmental corrosion. So those are the things that is some one has to understand, and exactly that is when our solution I'll discuss in terms of, you are removing the nickel, you are putting this barrier layer treatment, so it gives you the performance of nickel in terms of barrier layer for that copper atoms, but it gives you a outer layer gold, so you get the best environmental corrosion protection from a reliability perspective, as you brought up. But from a signal integrity perspective, it's very similar to immersion silver performance, because your signal is passing through either gold and most of it is passing through copper. So in that perspective, your signal integrity is as good as it can get, comparable to silver, but the reliability is always good because you have outer layer of copper and it is protected by underneath barrier layer treatment.
So, as someone who is much more of an expert on platings than I am, I'm sure you've done a lot of digging into the research literature, and you probably have found all sorts of ways people have tried to overcome this problem and eliminate
Yes.
nickel and still ensure that we have a highly reliable surface plating.
Yes.
You've gone one direction, which is using passivation to create a barrier layer. What are some of the other approaches that maybe haven't worked out or that others are trying to work on to then help us get to this next level with UHDI?
Yeah, absolutely, Zach. So people have actually tried this. This is not, this direction is not completely new. Exactly what you brought up. We took this path, but it has been explored previously. So there are two or three ways people, or two ways mainly people have explored. Is one is it's something called DIG, which is direct immersion gold. So what they do is remember in the beginning of our conversation I said that you cannot put immersion gold at that thin layer, because if you don't have nickel, copper will diffuse out to the top of the gold, the top surface of the gold layer, because it's only 50 nanometer, right? But direct immersion gold actually plates as high as 150 200 nanometer. So the idea is, even if it diffuses, we hope that for 200 nanometer it would not go all the way out, and then our application in terms of assembly or our application is not as will. So if it takes, in terms of an application, if you do a simulation or in real scenario, that if copper takes 5 years to come out to gold for 200 nanometer, that's good enough, because we need reliability only for 2 or 3 years or 4 years. So we will be fine. Let's put 200 nanometer, 250 nanometer of gold, right? So that is one approach people have taken. The second approach people have taken, hey, instead of using nickel as barrier layer, let's use palladium as barrier layer, like ENIPIG, but not put nickel in it, put electroless palladium directly on top of copper, and then, or directly, or they put some sort of a seed layer of gold, but mainly put electroless palladium and then put immersion gold. So they call EPIG or EPAG, that process. Now again, coming back to DIG, there is something I like to mention is with DIG, instead of 50 nanometer, you are putting 200 or 250 nanometer of gold. So your cost of plating almost automatically becomes 4 or 5 times more. So that is a major drawback when you do mass volume manufacturing for your products. But the second thing is also, when you have such a high gold count or gold layer with a micro BGA, when you are trying to do a solder application, that so much of gold may cause, I'm not saying it's the case for every scenario, but may cause such a small area, such a thick gold will get dissolved into solder, may cause gold embrittlement. So your solder may be subject to a brittle failure of some sort, because too much gold at that interface, and everything gets dissolved at the time of assembly. So there is an reliability concern with DIG, but also major is the cost concern. Now let's talk about EPIG. EPIG, electroless palladium immersion gold, as I mentioned, that also, not also, that actually add your cost even to another level, because palladium layer, as I mentioned, is 1.5 times the cost of gold. So you are replacing nickel with even more expensive precious metal compared to gold. So it makes your assembly even more expensive. That is one. And second is, even palladium has a concern of signal integrity. So you are removing nickel, it performs definitely better than nickel, palladium is, but it's not the ideal like gold or copper or silver. So you do still have signal integrity concern, especially you're going into higher frequency, into 20, 30, 50, 70 gigahertz. So in those scenarios, it's not the ideal replacement as signal integrity, because your performance is not as good as I mentioned, like likes of gold, likes of copper, or likes of silver. Yet the cost is exorbitant, because you are replacing nickel with even higher precious metal than than gold. So yeah, those are some of the alternatives that which are out there. And again, coming back to the alternative in terms of nickel free, is either you go completely gold free, which is a OSP and immersion silver. But we talked about some of their drawbacks from that perspective on the reliability side of things. So yeah.
So, of course, you being president of liloTree, I have to ask, how much of a positive response have you seen to your solution versus some of these other solutions that you mentioned? I get that, like DIG, super cost prohibitive unless you're at low volume. Epig, probably also not as cost prohibitive, but still cost prohibitive. So it sounds like
Yeah.
maybe one of liloTree's advantages is from the cost perspective.
Yeah. So actually, so couple of advantages I'll bring up is with all the benefits of ease of plate and for UHDI with signal integrity we talked about. But the cost is the liloTree's nickel free solution is actually cheaper, 20 to 25% cheaper than ENIC. So that is actually makes us a very, very attractive proposition from a cost perspective, because it's 20 to 25% cheaper than ENIC. And the second benefit is the typical gold plating happens with the cyanide based gold source, molecule or chemistry, whatever you call. So it's a cyanide based solution. Our solution, our gold plating solution, is completely cyanide free. It's more stable and it's actually cheaper to operate than a cyanide based gold. So from a nickel free perspective, I think we are sort of we call it as a chosen one, where whoever wants to do nickel free, they always use or opt liloTree's process compared to any other nickel free options out there. However, we are also sort of broadening the scope. There are some of the fab houses we are talking to, and we are actually in the discussion where they are considering to even replace ENIC with a standard boards, not necessary UHDI, not necessary the high frequency application. Even a standard board with a low frequency application and not necessarily UHDI are thinking that, hey, why are we using nickel or standard ENIC, which is even more expensive in the first place and has a reliability concerns at the interface of nickel and gold, as I mentioned, the black pad. And then also the third thing, getting a little bit technical, is your solder joint is a tin nickel intermetallics versus the nickel free option. You actually get copper tin intermetallic, which is much more stronger. And if the nickel free is cheaper, provides better reliability, and if it is sustainable, which is cyanide free, why should we even use traditional ENIC in the first place? So that is where we are actually foraying into. So for definitely from a signal, coming back to your question to answer, for a signal integrity and UHD application, definitely liloTree's nickel free is sort of a premier selection option. But we are also being considered as a traditional ENIC replacement solution as well for a traditional low frequency non UHDI boards as well.
Well, this is all extremely informative. We're just about out of time, but I want to thank you so much because I always feel like I learned something new whenever we chat. So thank you so much for coming on the podcast.
Thanks, Zach. It was great talking to you for sure, as always.
And to everyone that's listening out there, make sure to head over to the Peoria Sports Complex in Peoria, Arizona, if you happen to be in Peoria, Arizona, on March 26th, 2024, for the Ultra High-Density Interconnect Symposium, sponsored or put on by SMTA. You will get to see Kunal Shah at the symposium talking about all of the stuff that we've been talking about here today. To everyone that's out there listening or watching on YouTube, make sure to hit the subscribe button and hit the like button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.